Okay, we're back and we're live. You can stop sharing the slide. Thank you. Welcome, everyone, to the Tuesday afternoon Eastern Time press conference. It's actually not a press conference, it's a seminar for science writers. Get ready for Webb, the James Webb Space Telescope. I'm Rick Fienberg, I'm the AAS press officer, and assisting me this afternoon are the editor of AAS Nova, Susanna Kohler, who will be monitoring the Slack channel, and our AAS Media Fellow, Tharani Konchadi, who is a grad student at Texas A&M. She'll be monitoring the Q&A box. So a few preliminaries. If you have questions for the presenters today, I'd like you to enter them in the Q&A box, not in Slack. If you do enter them in Slack, Susanna will remind you to move it over to the Q&A box. And the chat feature is disabled for regular attendees. That's just for use by the panelists. We are recording and we are streaming live to YouTube. And now what I'm going to do is, since this is a seminar for science writers, it's not a session where news is being shared exactly, at least not in the sense of science news, but it's a sort of a backgrounder. The occasion, of course, is that at least as of this moment and as of the NASA town hall yesterday, this should be the last AAS meeting before the launch of the James Webb Space Telescope, which is currently scheduled for the end of October. So we're very excited. It's a mission we've all been looking forward to for many years. And so in collaboration with my colleagues at the Space Telescope Science Institute and NASA, we put together this wonderful backgrounder for you, this seminar for science writers on what to expect in the coming 6 months to a year. So I'm going to cede the MC spot here to my colleague, Christine Pulliam. She's the Space Telescope Science Institute News Center branch manager and also the JWST News Chief. She's going to get the ball rolling, and she'll be turning it over in turn to one of her colleagues in the newsroom, and she'll let you know who that is. So Christine, I'll turn it over to you.
Great, thank you, Rick. Yeah, I was going to introduce myself, but you have done that for me. So let me just say a couple of words about why we put together this workshop. For those of you who don't know, probably many people on this seminar do know the Space Telescope Science Institute, which celebrated its 40th anniversary this year, is the Science Operations Center for the Hubble Space Telescope. But we also conduct science operations for both the Webb Space Telescope and Nancy Grace Roman Space Telescope. And we're home of Webb's Mission Operations Center, which means we'll command and control the observatory. So in our role as Webb Science Operations Center, we've organized today's workshop. So with that, I'll hand it over to our moderator, Senior Media Relations Specialist Hannah Braun, who spearheaded this workshop and did all the heavy lifting. It's all yours, Hannah.
Thanks, Christine. So thank you to all the panelists for your participation in our workshop today. I personally think you guys did all the heavy lifting. We also appreciate everyone who made the time to attend. As Christine and Rick mentioned, we hope that not only will you leave this workshop really with building excitement for Webb, but also a better understanding of the themes that Webb's programs will investigate. So we'll start off with Eric Smith from NASA headquarters. He'll give a mission overview and update as to where things stand right now. Then Dan Coe from the Institute will give a background on Webb's planned studies into early galaxies and galaxy formation, galaxies across time. And then Ilse Cleeves from the University of Virginia will follow up with a discussion on Webb's goals when it comes to stars and planet formation. Then Nicole Cologne from NASA Goddard will cover exoplanet studies. And finally, Heidi Hammel from Aura will end with an overview of Webb's studies on the solar system. So additionally, before I hand it off to Eric, just wanted to mention after this session, if you wanted to explore more articles, news features, infographics, videos, we encourage everyone to go to webbtelescope.org. That's our website for Webb Science, where you can find more information. Here you'll also find our new Science Writer's Guide, which is almost an all-encompassing guide covering what any writer, journalist, communicator would need before thinking about what they need to cover Webb. So Susanna will also post that in the Slack, links to that in the Slack channel. So I'll pass things off to Eric now. Feel free to take it away.
Okay, thanks, Hannah. I'm going to bring up some slides here. So let me see if I can share them. Well, as Rick mentioned, it's really exciting to be talking about the hardware and the development status for the final time at a meeting like the AAS, where, of course, we're really about the science. And so what I wanted to do was just let you know what's in store for these final few months of development, which includes commissioning. That's a really important part of the story over the next several months. Development for us doesn't end with the launch itself, but after the period where we get the telescope ready for science. So just to let you know where we are today, all post-environmental deployments and the testing associated with them is complete. We just completed the last one of that, which was the telescope primary mirror wing deployments in May. And so the observatory works as expected after surviving the simulated launch that it underwent. Launch rehearsals are continuing at the Space Telescope Science Institute, where the mission will be run as well as the science program. And there's been a regular cadence of these practices, each one getting a higher fidelity as we proceed towards launch. Those of you who might have attended the Space Telescope Science Institute Town Hall heard a lot about the Cycle 1 program. And that is now well defined, and they are starting to put that into the system to see how the observatory would actually execute it. I'll mention a little bit more about that. The one remaining outstanding piece of hardware, we had some issue with the S-band transponders discovered in January. They've been repaired at the manufacturer. They're getting ready to ship them back. And then around the 15th of June, they'll be installed, and then they'll undergo testing at the observatory level. Of course, been tested at the box level at the manufacturer. Importantly, we are on track to be ready to ship by the end of August. And so that does support the October 31st, 2021 launch readiness date. Now, earlier this month, Ilse held a press conference where they talked about the Ariane 5 schedule. Their next flight is scheduled for late in July, and it typically takes about we're the third launch, and so it's about 60 days in between launches. And so we will follow the 2 launches that have to go before us. Now, if we look at the schedule, it's actually getting really simple because most of the work is behind us now. A schedule like this used to have swim lanes for ground system development. The ground system is frozen for launch. That's installed. The science timeline is now covered by the Institute presentations. And so what we just have are these final tests and stowing. Now it's just really stowing, and then launch site processing. So let's jump down one level into that blue box, which are the stowing steps. This week, we're up there finishing off that blue box. We will deploy the tower. DTA stands for deployable tower. We'll do that this week. Then we go into a partial stow of the unitized pallet structures which hold the sun shield, and that's to install the last 23 membrane release devices, stow the tower, and then it's really just all about stowing and getting ready for launch. The activities here are somewhat in parallel, so it's not exactly as serial as it's depicted. These are just major flows, but some of the things on that bottom row are actually already underway. The final MLI, multi-layer insulation, is going on. Some of those radiators, the DERSs, those are being installed already. So we're making good progress towards that August ship date. And once we get into that last blue box, that actually takes us into what you might think of as activities for Karoo. That last blue box is the first box on this chart. O-STARS is the acronym for our shipping container. We load it there, we put it on a ship, it travels down to South America. The first 2 weeks or so of the activities are maybe 21 days, are Webb-specific activities with the payload. And then after that, we go into the normal flow of activities associated with any payload that launches out of French Guiana on an Ariane 5. I mentioned commissioning. This is a really important point that I think science writers will help NASA tell the story of what happens after launch. What you see is a timeline here. It's about 180 days of activities that have to happen after we launch before we're ready to do science. Webb's an infrared mission. We're passively cooled, and we have to control very carefully how various pieces of the observatory cool down during this commissioning period. And so you don't just let the whole thing drop in temperature. And so it's a very careful orchestration of how the vent pieces of the telescope cool down and get activated. And you can see the sequence here. First, SC is spacecraft commissioning. Then there's telescope commissioning, when we actually make these 18 mirror segments act like one giant mirror. And then once that's done, then we need to go into the science instrument commissioning and to calibrate things like the sky backgrounds, any stray light, the sensitivities of the instruments, the various modes of them. And so all these details have to fall into place before we're ready to turn it over to the science community to use. Speaking of the science community, we know what they want to do with it. As we've seen in cycle 1, interestingly enough, about 50% of the accepted proposals are in 2 themes: galaxies in the interstellar medium and exoplanets. So while this mission was not initially conceived as an exoplanet mission, it's going to be doing a lot of that, and you'll hear more about that later. Another fascinating thing for me, at least, is to see how the science community wants to use this. They really want to use this as a spectroscopy machine. So they're going to be teasing out the physics of what's going on, not only for objects in our own solar systems, but in the distant universe. So this was fascinating for me to see that more now in cycle 1. So I just want to give you this quick mission status summary before we talk about the really exciting stuff, which is the science. And that is the pre-launch performance predictions are what we have been promising the science community for all these years, and it's what they require to do their science. Cycle 1 observations are beginning to be put into place, and the final hardware preparations are nearing their end, so that we can get on to the exciting stuff which comes next. And that we'll hear from Dan about that.
All right. Hi, everybody. Great to be here. Let me go ahead and share my screen. And all right. So I work at the Space Telescope Science Institute along with Hannah and Christine, where I'm very excited to be an astronomer and work on my own observing programs with Webb, and also support the community, support other astronomers with their observing programs. So, wait, hang on. All right, so we've nearly completed writing our cosmic history. Hubble has looked back in time to observe distant galaxies 97% of the way back to the Big Bang. What's left is the first chapter, the first 400 million years. We've yet to see a single object as it existed during that time. And a lot happened then. The first stars and the first galaxies lit up the universe. Webb will reveal for the first time the first galaxies that formed during these eventful early years. Hubble has looked back in time by taking images like this, the ultra deep field. We find some galaxies that look familiar, like spirals and ellipticals, plus thousands of more distant tiny galaxies in this small patch of sky the size of a grain of sand held at arm's length. In its first year, Webb will re-observe this same patch of sky, revealing galaxies even smaller and more distant than Hubble can see, thanks to Webb's larger mirror and longer wavelength infrared vision. Webb will also use nature's telescopes, gravitational lenses, to magnify the distant universe, revealing ever more faint and distant galaxies. Here we see what this looks like with Hubble, and this is what I work on, and I'm very excited to do the same thing with Webb. But with lensing, there's a trade-off. Magnification sacrifices search area for the depth that reveals smaller galaxies. So which effect wins out? Well, it depends. But in the early universe, there are many minuscule faint galaxies. So according to my calculations, I predict that lensing will be the key to discovering the first galaxies with Webb. This will fuel a friendly competition between blank fields and lensing, as we've long had with Hubble. And as you can see here, these are the 2 most distant galaxies known. My friend Pascal Oesch discovered the galaxy on the left that edged out my discovery on the right for the title of most distant galaxy known. So the blink fields are winning for now, but I predict that won't last long with Webb. And we'll find out. Of course, there will be many of great discoveries in both the blink fields and the lensed fields. So what have we learned about these early galaxies so far, and what questions remain? Well, they were extremely small, the size of individual star-forming regions in spiral galaxies like our own Milky Way or M74 shown here. But are they really such simple clumps? Or are they more chaotic, like this dwarf galaxy, much closer to home? And that's what we expect from simulations of the early universe, as you see here. Hubble may just be showing us the tip of the iceberg of these small distant galaxies. Webb will reveal far more detail, including fainter, older, and redder stars invisible to Hubble. But Webb's real superpower will be spectroscopy. They say an image is worth 1,000 words and a spectrum is worth 1,000 images for all the detail it contains. Spectra aren't as pretty as images, but we'll try to make them so, and we'll need to tell their story well. Most of Webb's great discoveries will likely come from spectra. Spectra will tell us what early galaxies were made of, how actively they were forming stars, and whether they had enough power to reionize the gas around them. When we say Webb promises us to reveal the first stars, we've often understood that to mean stars within the first galaxies. But in recent years, gravitational lensing has given us a new hope. Hubble has revealed 3 individual stars with extreme lensing magnifications, enabling us to see them at great distances. They all date halfway back to the Big Bang or more. Webb will reveal ever more distant individual stars that may be among the first stars to form in our universe. What secrets might they hold? We may find that they are composed solely of the primordial elements, hydrogen and helium. But more likely, we won't see the very first stars. They probably lived fast and died young as supernovae, enriching their surroundings quickly with heavy elements. So the early stars that we do see may already contain the heavy elements found in our bodies, the stuff of life. These are just some of the many questions Webb will address as it transforms our understanding of the early universe. I'm very excited to see what Webb will see, and I'm happy to take your questions at the end. Thank you.
All right, hello everybody. I hope you can see my slides all right. I'm Ilse Cleeves, and I'm excited to be here to tell you a little bit about some of the exciting new frontiers that lie ahead in the field of star and planet formation. So we're in an exciting era of exoplanet discovery, and one of the biggest questions is, what are these planets' origin stories? How common are, potentially habitable compositions for these planets? And so I'll take this talk to briefly review some of the recent progress that set up some of the most interesting, outstanding questions that JWST will hopefully be able to shed some light on. All right, so one of the biggest questions that in this field and all of astronomy is, are we alone? How much does it matter that we happen to be, our Earth happens to be orbiting a G-type star and that has this particular configuration of planets that we do in sustaining and supporting our habitable planet Earth? A more specific question in this matter is, how often do planets, both at home and abroad, have the right stuff to support life? Planet formation results in a wide variety of outcomes, and our solar system has no shortage of wonderful examples of this amazing diversity. So some of the key scientific questions we're really interested in this field is, first, how do stars and planets assemble? And second, what is the chemical history and the makeup of the interstellar materials from which stars and planets form, shown in this beautiful image of the Orion Nebula? And so over the next couple of slides, I'll lay out where we currently stand in our understanding of star and planet formation and where we're going. So, for example, we think we have the standard recipe for forming a star and planetary system down pat. So you start off with this initial collapse of an interstellar cloud to form a new star or multiple stars. And so as the cloud collapses and rotates, it'll set up naturally a disk from which planets begin to form. And so within these stages, these phases, we think we understand a number of the components. First, we understand star formation fairly well within our own galaxy and in extragalactic settings. And while we know the efficiency of converting interstellar gas into stars isn't high, we do know that stars form on a wide variety of environments and scales, from the outmost regions all the way into the inner regions of galaxies. And I particularly love this image, if you can see my mouse, on the bottom right down here. This is our galactic center, seen with ALMA and the radio. And you can see all of these little jets lighting up from young protostars that formed in the last million years or so, so showing us ongoing planet formation, even in our galactic center. So star formation is fairly robust, and so is, we think, planet formation too. So exoplanets seem to be everywhere that we look, even in the galactic center. And so from this, we think planet formation is a fairly robust process. Disks around young stars, where these planet-forming environments that I mentioned earlier, also seem to be pretty common, especially in low-mass star-forming regions where over 70% of the stars host pebble-rich disks. Surveys of the compositions of disks are still sort of in their infancy, just beginning, especially with new telescopes, but we're seeing some really interesting trends that the chemistry of disks around stars that are different from our sun, including low mass stars, seem to be actually pretty similar to that of sun-like stars. And so maybe there's the same sort of good stuff around to form those future planets. And so a lot of what we've learned, especially in the last 10 years, has been owing to this new facility, the Atacama Large Millimeter Array, or new-ish now, I guess, facility. We're in this wonderful era of ALMA that's really zoomed in our picture of star and planet formation, both in physical and chemical ways. So here's just a couple of examples of where we are with ALMA now. ALMA's been able to map out this sort of star formation potential, especially on galactic scales and extragalactic settings. Beautiful images have come out of the FANGS collaboration showing cold molecular gas. ALMA's imaged the outflows of young stars that are currently in the assembly process. This is a beautiful case of DG Tau B. And on the right, we've had a ton of surprises. This is an incredible case of a filament feeding a young star and forming planetary system. So the star itself is not done growing, and within the disk of this young star, we already see evidence of a companion, a substellar companion, likely somewhere a few Jupiter masses to maybe tens of Jupiter masses in size. And so ALMA has been wonderful in these imaging, in these beautiful images and revealing all these processes. But honestly, it's actually created many more questions than answers, which is what a good facility does, right? And so I don't intend for any of you to read this entire list of questions here, just mostly to be overwhelmed by how much we still have to learn. And that's why I'm personally very excited about JWST. It provides the unique tools, both the imaging capabilities, the spectroscopic capabilities, to answer a lot of our open questions in greater detail than possible. And so I'm going to go through a couple of examples of these more targeted JWST-related questions in the next couple of slides. And actually, just to point out, these are targets of, these are scientific questions that JWST will be able to answer on day one, and already are in some cases planned in the coming years through ERS, GTO, and GEO programs. So one exciting area I want to highlight is the field of stellar assembly. So here you have a beautiful overlay of the radio image of HD 163296 and its gorgeous collimated jet seen in the optical and sulfur-2 emission. JWST will have the ability to map these kinds of outflows, these powerful outflows that sculpt their local environment through hot water, CO, ionized atoms, and many other tracers. And so this will be really critical for understanding the power, both the mass budget of star formation, as well as the processes that sculpt star forming regions. In addition, stars, when they're young, they don't pile up mass smoothly. They probably do it in bursts, and we know in some cases they definitely do it in bursts. And so JWST is really well poised to investigate the chemistry of outbursting sources and even map like the mineralogy of minerals that are being cooked by the early furnace of the outbursting young stars. On the topic of the warm phase chemistry, later, once the star is kind of settled down, JWST will be incredible for mapping out the chemistry or constraining the chemistry, characterizing the chemistry, I should say, of the inner terrestrial planet forming region. And so Spitzer already discovered water, organics, hydrocarbons, all within a few AU of stars like our sun. And so from this, we know there's a lot of really interesting stuff there that could be seeding future terrestrial planets that are in formation. But JWST will really improve our ability to do this in leaps and bounds. So for comparison here, you can see sort of what what Spitzer could do previously, and this is a slide credit Klaus von Tabadan. And on top are models, predictions for JWST Miri, and how we'll be able to actually finally resolve all of these different species apart and to say so much more about them and also learn more about the isotopic history of these molecules. And so this will be really crucial for directly comparing to exoplanet atmospheres, especially those close to their central stars. I'm personally very excited about what JWST will do for the icy universe on larger scales for icy molecular clouds. We know the interstellar medium, the ISM, is cold. Ices are a major constituent seen in Spitzer spectra, but we've had relatively limited information on these larger cold molecular cloud scales. And so you can see sort of the ice features that have been identified in the past. JWST will be incredibly sensitive and will unlock many of the complex species that we didn't really fully understand before, and also the isotope ratios of some of these molecular species. And that really imprints the history or the formation history of these molecules. I'm personally also excited about the ability for JWST to constrain the ice composition of disks, which has been done in the past, but it's really not been unlocked to its full potential by any means. And so JWST will be able to let us find trace species like CO2 and methanol. This is beautiful work done here by my postdoc. And in addition, JWST will let us map the ice distribution to see whether it's sort of smooth or clumpy or follows rings and structures in the disk. And so this is something we're excited to do as part of the guest observer program in the coming cycle. And so with that, I'll summarize. We have the last decade has brought major advances in the characterization of planets both at home and abroad around a wide variety of stars. The last decade has also improved our ability to both observe and model these objects and understand them at a deep physical and chemical level. But it's brought many, many more questions than it has answers. And so I'm excited about JWST because it has this key imaging and sensitive spectroscopic capability that will really truly unlock star and planet assembly on many fronts that I tried to highlight here. And so these are the kinds of multi-wavelength observations that are crucial to filling out this picture, to answer the big questions, including, one of my favorites, how common are the formation of habitable planets in our galaxy? And so thank you, and I'm happy to take questions at the end.
All right, I am up next, and that was a perfect setup for what I'll be talking to you about in terms of actual fully formed exoplanet science with Webb. So first, I wanted to start off with following up Ilse, who gave a perfect talk about what we're going to learn about planet formation with Webb. So I'm not going to talk too much about that, but that is one of the key components, of course, of exoplanet science with Webb, is to study how exoplanets form and evolve over time. So exoplanets typically form within disks and then often migrate inward to the current orbits where we observe them. And so Webb will really be used to investigate these processes by observing a number of star systems with disks around them to learn more about the structure and composition of the disks, as we've heard, and then how that connects to the presence and evolution of fully formed exoplanets. But once you have a fully formed exoplanet, what Webb will spend a lot of time on as well is to explore the current day composition of these exoplanets and specifically of their atmospheres. So Webb's optical and infrared observations in particular really probe deep into an exoplanet atmosphere, and we can use Webb to identify the different elements and molecules, as well as the presence of clouds and hazes that are in the atmosphere. So we can really use Webb to get the detailed structure and composition of these atmospheres. So how do we study exoplanets with Webb exactly? Just to briefly go over this, direct imaging is one technique. And this is a technique where we're directly resolving a light from either a disk around a planet, or excuse me, around a star, as we heard, or resolving a faint exoplanet around a bright host star. So basically, you're using some technique like coronagraphy to block the light or minimize the light from the host star. And then you can see the faint companion. And then the resulting image of the planet in this case can then be analyzed to reveal the composition of the planet atmosphere in particular. And then as another kind of example to follow up on the previous talk, these direct imaging techniques will also be used to study disks where planets are presumed to be forming. And this is one example of an ALMA image of a target that Webb will actually be looking at in the first year of science. So this is an image, again, from ALMA, but it's showing you what ALMA can see, which is a lot of the outer regions of the disk around the host star. And so Webb will really complement this and probe more of the inner disk as well, to thanks to its infrared sensitivity and resolution. So really, thanks to Webb's larger mirror and the stability of the telescope, and also its access to infrared wavelengths of light, Webb really offers some unique advantages for imaging exoplanets, as well as disks where planets are forming. And the infrared is really especially an ideal place to image exoplanets, because that is the wavelengths where young and newly formed exoplanets are really the brightest. So they still have some internal heat from their formation. And there are around 40 different stars that will actually be observed in Webb Cycle 1 with direct imaging techniques. And these include young exoplanets like the one shown on the left, bottom left here, HIP 65426b. And it was previously discovered by a ground-based telescope. The discovery image is on the left. And then there are two simulated images of what Webb will see, or should see, with NIRCam and MIRI. And then Webb will also be used to search for previously undiscovered exoplanets. So we know that exoplanets are common, should be everywhere, and Webb will be used to search for such exoplanets that we haven't yet discovered with current facilities. And one of those searches will be around our nearest neighbor, Alpha Centauri A, where we expect to be able to search for giant exoplanets around that star. But moving to a different technique, Webb will also use the transit technique, and that's a very indirect method to study exoplanets. So we're not resolving an image of the planet, but instead we're seeing the effect the planet has on the star. And so the planet blocks some of the light from the star when it passes in front of it from our point of view. And then when you look at different wavelengths of light using spectroscopy, then you're able to see the planet's atmosphere, the impact that has on the starlight as well. So there's a lot of observatories that can do this technique already using the transit method, and Hubble's one of them, as well as ground-based observatories. But Webb really offers some really precise, sensitive infrared data that these other observatories cannot access. And so at the wavelengths that Webb can access, we will be able to use the transit method as well to search for absorption from molecules like water, but also carbon-bearing molecules, carbon dioxide, methane, and more, where that can tell us about the planet's potential formation history, as we heard in the previous talk. So a couple facts about the Transiting Exoplanet Science Program. There are nearly 70 different transiting exoplanets that will be observed in the first year of science. And I've broken down the rough numbers of these sizes of planets that will be observed. But I want to point out that a majority of Webb's targets, at least in the first year of science, are really small, potentially rocky exoplanets. So that's really exciting. And that really goes to show that Webb is offering the first avenue for studying these small planets in detail and in bulk. So these targets include all 7 planets within the TRAPPIST-1 system. TRAPPIST-1 is a very small and cool star that is very different than the sun, but it does host multiple planets within the habitable zone region around that star. And so what that means is just that the planets in that region have temperatures that are sufficiently low that liquid water might exist on their surfaces. So Webb will be able to explore whether water vapor is in the atmosphere of these planets. And on the other hand, another small planet to be observed by Webb is shown on the right, and that's known as 55 Cancri E, and it's a super hot planet that is so hot it might actually be raining lava. So there's a nice diversity of planets to be studied in cycle 1. And then finally, I wanted to note that of the transiting exoplanets to be observed in Webb's first year of science, 25 of them were discovered by TESS, the Transiting Exoplanet Survey Satellite. And TESS launched in 2018, and it's been scanning the sky, hunting for small transiting planets around bright nearby stars in particular. And it really has delivered. Many TESS planets make great targets for Webb, and that's clearly shown here by the number of TESS planets that'll be observed by Webb. And we'll get to explore their atmospheres, many of them for the first time ever, and others in greater detail than ever before. So these are a few examples of small planets and small planetary systems that Webb will observe. And I did note the one on the right, WD 1856b, is not a small planet, but it's a Jupiter. It appears to be a Jupiter-sized planet orbiting a white dwarf, which is really rare and really exciting. So just to sum up, Webb will provide a new view of both disks where planets form, as we heard, and of exoplanets and their atmospheres. And in Webb's first year of science, nearly a quarter of time will be spent observing exoplanets. So it really is a big chunk of the program that we're really excited about. And we're ultimately going to get new information about how these planets formed and evolved based on their current day structure and composition of their atmospheres, while also discovering new exoplanets that we have not yet discovered with other telescopes. So with that, I will hand it off to Heidi to talk more about the solar system.
Great, thank you so much. Let me pull up my slides here for you. And we will try to start the screen sharing. I can't see the screen place to start the slideshow. We'll do it that way. Okay. Play from the start. Great. Wonderful. So thank you all. I'll close out here by talking about solar system science with the James Webb Space Telescope. One of our key science themes is, in fact, planetary systems and the origins of life. And you just heard a really great talk from Knicole about the physical and chemical properties of other planetary systems. But the phrase "including our own" is also part of the theme for James Webb Space Telescope. And so that's what I'll be talking about today. Within our solar system, you remember that James Webb is going to be located at the Earth-Sun Lagrange 2 point. I just put a tiny little web there if you can see the cursor. And because of its location there, sorry, I did a bad thing. What that means is that my bad thing made it impossible for me to advance my slides. So I'm going to try to start that again. And I apologize for my glitch here. I will try to start again. Slideshow. Play from current slide. Hopefully this will work. Is that working? Can you see them? Oh dear.
Yes, we see them.
Okay. I'm not, I apologize. I'm having some difficulty on my end, which is unusual. So I'm gonna.
You might want to just try using your arrow keys instead of clicking.
Those are what I'm actually using.
Okay.
So
well, never mind that then.
Yeah. Let me try one more time. Gonna go back and play from the start, and hopefully all will work now. Okay, we're good. All right. Sorry about that.
Except that we don't see your slides.
You don't see my slides now?
No.
Oh, good Lord.
Ilse suggests going out of slideshow and going into presenter mode, and then choose slideshow auto advances. That might work for you.
Okay. You know, I use Zoom day in and day out, and I've never had this happen to me before. So it looks to me like I am out of this now. I'm going to try one more time to share my PowerPoint. Can you see it?
Yes.
I'm going to now say play. Can you see it now?
Yes. We're back to the first slide.
Great. All
Second
right.
slide, third slide. All right.
All right. I'm not going to touch my cursor ever. All right. I'm just going to hit the arrow key. All right. What this means, because we're located at L2, is that everything basically inside of L2 is not visible to us. Our sun shield will block the Earth, the Moon, Venus, Mercury, and the Sun. But everything else is available to James Webb for study by the telescope. And that includes near-Earth asteroids, because there are certain times when those near-Earth asteroids are not interior to us, and we can see them. Okay, so I want to mention there's 3 flavors of proposals. You heard some of them mentioned by the earlier speakers. There's guaranteed time observations. Those were the teams who were originally selected to help build Webb. And Jonathan Lunine and I were planetary scientists selected for that. There's also early release science observations. 13 of those were selected, and one of them is solar system. And then there are geo and archival, guest observer and archival. And this is where the community members write proposals. And there were 22 of those selected for solar system science. I used to tell my community members, you got to buy a lottery ticket to win the lottery. And I showed this slide, Lucky 7. The takeaway for that is that was prescient, because 7% of the cycle 1 time went to solar system observations. So that's how much time in cycle 1 will be used to study objects within our solar system. And you will get a copy of these slides later. They can be available to you, or you can contact me if you want them. These are all of the solar system science slides. It's an eye chart, but all of the names are there and all of the objects are there. So because I'm the PI of our guaranteed time observations, I want to note that I actually gave all of my solar system time away to all of these community members who have created a fantastic program of exploratory solar system science with James Webb Space Telescope. So I'll talk a little bit about their science, and I'll also talk a little bit about some of the general observer science from the community. So it'll be a little bit of a mixture of both. Let's start with Mars. Some of you may be saying, why should we take our precious James Webb Space Telescope and look at Mars? Haven't we sent a gazillion spacecraft there, landed, orbited, roved, and now flown helicopters in the atmosphere? The answer to that is, yes, we have done those things, but our space telescopes provide context information that is not always available to an in situ rover or an orbiter that may only sample small parts of the atmosphere. So on the right-hand side, you can see Mars images taken with the Hubble Space Telescope over decades. And you can see the evolution of the planet's atmosphere and polar caps. And so this is important context information for the rovers, the helicopters, and the orbiters. The cartoon on the left shows you a bar that is the slit of the near spectrometer, and it shows you how we'll be able to scan across Mars to do atmospheric and surface chemistry. And there's also a little crosshairs with a dot. And that dot is the resolution element that James Webb Space Telescope will have on Mars at certain times in its orbit. And so with this capability, we can create global maps of the dust in the atmosphere, global maps of the surface composition. We can use our spectroscopic capability to map out water, carbon dioxide, hydrocarbons, and other capabilities of the atmosphere over time and as the planet rotates, and use this information to help inform our local missions. Here's an example of a spectrum of Mars, showing you the kind of materials that we may be sensitive to: ethane, water, carbon dioxide, hydrogen chloride. And over there on the right, you see the big red methane. Those of you who follow Mars science know that that's a a perennial question about the methane in the atmosphere of Mars, whether it's stable, it seems to vary. Why does it vary? Over how large position of the planet does it vary? James Webb Space Telescope will be able to address this question. And so it's really potentially very interesting. Moving outward, this is a lovely Hubble frontier field. And all those strange arcs and swirls you see are asteroids that have photobombed the frontier field. One person's noise is another person's signal. And so in the solar system, of course, we want to actually study those asteroids. These are the examples of some of the kinds of questions that we will be exploring with Webb. How does space weathering affect the surface of the asteroids? Are all the spectrally red surfaces due to organics? What volatile species are present on the atmosphere, on the surface of an asteroid? These are all the kinds of questions we'll be exploring. Here's 4 different asteroids that I showed you just to give you a sampling of how very different asteroid spectra may look. You can see that different compounds really do a number on the infrared part of the spectrum and allow us to, at a glance, characterize different asteroids into their respective classes. And you notice there's a section that's blocked by the Earth's atmosphere. There's actually a very interesting hydroxyl line that takes place right inside that part of the spectrum that Webb will be able to study. And this really gives us insight into the hydrogen and oxygen content that are trapped in these various asteroids that we'll be studying. So it's a very interesting perspective. Those of you who know me know that I'm very interested in giant planets. And of course, there is a very robust giant planet program being led by Lee Fletcher at the University of Leicester. Matt Tiscarino will be studying the ring system and small moons of Saturn. And Glenn Orton will also be working on these planets as well. I have to say, Jupiter's hard. Jupiter's bright. And so we actually have to play some interesting tricks to be able to not saturate our detectors with the light of Jupiter and Saturn. No, but we have clever ways of doing this by putting us into sub-array readouts. And by doing that, we can keep the flux down low enough to actually get spectra from Jupiter and from Saturn. We'll be, one of those ERS programs is specifically looking at Jupiter's Great Red Spot. Maybe we'll finally know what the chromophore is that's causing it to be red. That would be an interesting question to finally have the answer to. I like to joke that the mid-infrared camera, the MIRI camera, integral field unit, which is represented by the blue, green, yellow, and red squares, was designed for the planet Uranus. You see, it's a beautiful match to the spatial scale of Uranus and its ring system. And so we will really be doing some fantastic spectroscopy of the upper atmospheres of Uranus and Neptune. We will be studying the high atmospheric circulation of that planet. We will be looking at the orthoparo-hydrogen ratios, looking at disequilibrium species, we hope, not yet detected in these planets, but expected if you look at the simulated spectrum that you see on the top of your screen there. Things like phosphine and ammonia, which have been detected on Jupiter and Saturn, we speculate are there in Uranus and Neptune. And Webb will probably be the first telescope to be able to actually detect those chemical components. We will also be exploring ocean worlds with Webb. The Guaranteed Time Observing Program is going to be looking at the plume material that was on the left side detected with Hubble in the ultraviolet. And on the right side, you can see a Saturn Cassini image of its moon Enceladus showing you directly the bright plumes that are water that is spewing out through cracks in the surface. We plan to try to put our beam on the plume areas, both for Europa and Enceladus, and to detect whatever we can in those plumes. And I won't say it's going to be easy. This is an exploratory program that we're doing with the guaranteed time, because this is a very challenging observation. We're not sure we'll have the sensitivity to detect it. And those of you who follow this story for Europa know that the plumes on Europa don't seem to always be there. And so we have to get lucky. But as this spectrum shows you, if we are successful, not only will we be able to detect the water itself, but we may be able to detect trace compounds that could be indicative of the carbon-bearing species that could be present in this plume material being ejected from Europa and Enceladus. And so that gives us clues to their potential habitability. It could give us clues as to what is driving these plumes. It could help us understand the stability in the evolution of these plumes if we can detect them and determine their chemical composition. So it's a very interesting program. Titan, of course, has been very well explored by the Cassini spacecraft, but Cassini, of course, is no more. It was deorbited into the atmosphere of Saturn. And so we will be looking at Titan with James Webb Space Telescope. And it is a large enough moon that we can actually both spatially and spectrally resolve Titan. And in this simulation of the spectra, you can see that you can distinguish between the spectrum of clouds, the spectrum of dunes on the surface, and the spectrum of lakes. And so with adequate observations, both spatial and temporal, we may be able to tease out changes in the atmosphere and surface of Titan that have taken place since the end of the Cassini mission. So that's a very intriguing ability to study this evolving world, Titan. Comets, they're very wonderful and beautiful, and we have a robust program to study both the chemistry of the comets and also look at the dust environment around comets. The infrared capability is crucial for this, and so there are several programs devoted to studying a variety of known comets. And last, but certainly not least, the Kuiper Belt. When I first started working on Webb more than 20 years ago, the Kuiper Belt was thought to be the prime solar system science for Webb. Almost every known Kuiper Belt known to date is accessible to Webb because it is such a powerful tool. And so we're very interested in the spectral characteristics, not only of objects we've already explored, like Pluto, but objects that we have barely begun to explore, like Hammel, Orcus, Eris, and the very distant and strange object Sedna. All of these will be targeted by James Webb Space Telescope during its first year to study the surface composition and whether it changes with time, and to learn about the various classes of Kuiper Belt objects. And I wanted to put a shout out to the DISCO's TNO's team. This was an approved large program led by Nimi Pinilla Alonso and her colleagues, more than a dozen of them. There's a few shown here. They have been awarded 98 hours to characterize the spectra of 59 different TNOs, different from the ones that we're already planning to do with the guaranteed time that I mentioned before. And so there's going to be a huge explosion of our knowledge of the Kuiper Belt from James Webb Space Telescope. And I just wanted to end with, what about the rare or the unusual? What if the comet of a century comes by? We're ready. Program 1253 is a target of opportunity proposal. So if a comet comes by that's spectacular and amazing, we will be ready to observe it. Another interstellar object like Oumuamua or the comet Borisov, if that happens, Webb is ready. Program 2337 is a target of opportunity proposal that will characterize the next interstellar object to come by. And of course, near and dear to my heart, what if there's another impact on Jupiter like we saw back in 1994? Webb is ready. Program 1424 is a target of opportunity proposal so that if there's another impact on Jupiter, we are good to go. So in summary, I and my colleagues are looking forward to a very robust and rich series of Webb observations all across our solar system. And with that, I'll turn it back to our moderators.
All right. I guess we can just jump right into Q&A since we're short on time. And because we have a couple of questions from the same people, I'll try and go through, get a question from everyone first. And if the folks running the show think it's okay for us to go over, we can maybe get through all the questions.
Yeah, we can go over by about 5 to 10 minutes.
Brilliant. All right. So Eric is probably the best person to answer this question. I imagine anyone can jump in. This question comes from Pamela Gay of the Daily Space. There is a petition to rename JWST. Is there any hope that during this Pride Month, or at least around launch, we'll get a new name?
So NASA is well aware of the concerns that have risen about James E. Webb, the man, and we're looking with historians to examine his role in government. Of course, NASA named its next generation observatory, the James Webb Space Telescope, after its second administrator, who had helped to establish the Apollo program that landed humans on the moon. The agency made the naming decision in recognition of Webb's role in retaining an active science program. Webb's work as administrator laid the groundwork for today's accomplishments, and science remains a critical part of NASA work to understand the universe and advance exploration. This is not a decision that the program office can make, or the astrophysics division, or even the science mission directorate. This is an agency level decision, and it's being considered at that level.
Thank you. This one is for anyone from Ethan Siegel of Forbes Starts with a Bang. Do you have any visuals to share of mock JWST data to indicate how the generated images will appear to us, with Zult leaving and having previous, quote, non-Hubble images with questionable palette choices? How close is the internal community to coalescing on what Webb's assigned color images will look like?
I can jump in there, and then if our panelists have anything they wanted to add, they can certainly do that. We all expect that the images that come from Webb are going to be just as stunning as those that we've seen from Hubble. They are undoubtedly going to have a different flavor than Hubble's iconic images, not only for the obvious reason that Webb is an infrared telescope, but also the cameras have many more filters than Hubble's cameras. So it will probably be something of a challenge to combine them. As you know, any image processing, Hubble images, other astronomical images, it's both an art and a science. But our image processing team is definitely working diligently to make sure that Webb's data is converted into the most beautiful and scientifically interesting images that we can possibly generate.
Like I say, I did show a simulated color image by the NIRCam team, and showing what they expect to observe, and I thought it looked great.
Thank you. This question comes from Alex Witz of Nature, and it's directed at Knicole. What's the time frame in which JWST exoplanet discoveries will be rolled out? How quickly will some of these cycle 1 observations translate into, for example, detecting something like an Alpha Centauri A planet?
Yeah, that's a great question. First, to address the Alpha Centauri A, I should note that survey to search for a planet will be using MIRI chronography specifically. And the goal there is to detect an older or mature gas giant planet down to something like half a Jupiter in size, if it's there. So that's what that program will be doing. And so there's a specific team that proposed that program, and a lot of, all of these imaging programs to search for planets go to a certain team. And so it's a combination of when the observations actually get scheduled. And then once they are scheduled, the good news is that the data comes down pretty quickly from Webb. But then there's a process to actually analyze the data, of course, and especially with the first discoveries, or with tricky observing modes, there will be some careful analysis ongoing. So I can't speculate too much of how long, it will take to analyze data, maybe a few months, hopefully not much longer, but it's also an artifact of when things get scheduled. So there's a couple of factors at play, but if we're lucky, that might happen early on in the first cycle there. So within a few months after normal science operations at best.
Thank you. This question is from Don Hladiuk for CBC, and it's directed at Heidi. Will the JWST be used to look for a possible new target for New Horizons in the Kuiper Belt?
Good question. Well, I want to share we're already looking for new targets for the New Horizons spacecraft with current active telescopes, the Hypersys PrimeCam on Subaru, and we found the previous one with the Hubble Space Telescope, of course. And so I think that if we are still looking when Webb is launched and there is a good reason to use Webb, I'm sure that the team will propose to do that. And that proposal will be evaluated in the context of all the other science proposals that we get. I'm hoping we can find one before that with the larger telescopes that we're using already, and with Hubble. So we'll see. We'll see.
Thank you. This question likely best directed to Eric from Ethan Siegel. Forbes starts with a bang. There's a lot of uncertainty surrounding the lifetime of Webb, which seems like it's limited by the onboard fuel/propellant necessary for pointing the telescope. Can you give an optimistic upper limit for Webb's lifetime? And also, don't tell me a lower limit. I know a bad launch could be ruinous.
Yeah, great question. Actually, one of the most important things that happens shortly after we launch, about 12 hours or so, it was on one of the charts there, is called a mid-course correction. And that would be a burn or use of some of our fuel to give us an optimum trajectory to L2. The smaller, if we use very little fuel for that, that means that we will likely have more than 10 years of lifetime. As Ethan pointed out, we have fuel for 10 years of lifetime, assuming some nominal observing program. So I suspect if we get a very good launch, don't have to use a lot of fuel during the mid-course correction, and over time learn how to operate the telescope in a way that minimizes the buildup of momentum in our reaction wheels, which we have to use fuel to push against to desaturate them, that we could get more than 10, and I'm going to say, into the teens of years. But that's my optimistic hope, and I sure hope we get to do that because of all the things that people told you about they want to do.
Thank you. This next question also comes from Ethan Siegel, and it's directed at Dan. In the case of Pascal Oesch's record holder GN-Z11, isn't that also a lens galaxy, just lensed by objects in the field? And if so, how much lensing do you typically get in a blank field relative to a known lens field?
Right. So that was in a blank field, and the candles field, and so you might get a few percent of magnification compared to the galaxies that I look at, which might be magnified by a factor of 10 or usually a factor of few, maybe up to 10 or a few tens. Yeah. So yeah, we that was very well deserved discovery from Pascal, and we have a lot of fun with it. And thanks for all the questions, Ethan. I wish we were in person. Hopefully we'll get to see in the winter AAS.
Thank you. This next question comes from Alex Witz, and it's directed at Eric. How do those transponders travel from TASI to Northrop Grumman? Just curious if they are escorted, going via FedEx, or what?
They were shipped over the way of spaceflight hardware is shipped, and they will come back the same way. So I guess it's not a very exciting answer, but they're just shipped as spaceflight hardware normally gets shipped.
Thank you. I suppose, Eric, you could also answer this last question from Pamela Gay of the Daily Space. You didn't mention the fairing issue. Can someone please address concerns about the last 2 missions that grounded the rocket since August 2020 and plans to look and see what happens in the next 2 launches?
Sure. We, as I alluded to in the first slide, we follow 2 launches that will be coming up in July is the first one, and they will have made modifications to the fairing to account for the anomaly they experienced last year. And so Arianespace, ESA, and NASA will look at the data after those launches and make sure that it's safe for Webb to launch using those. So that's just a part of the plan.
Thank you. I don't see any other questions, so I'll hand it off to Susanna, who's been monitoring the Slack.
Nothing over here.
As it should be. That's great. Well, thank you all for putting up with us going a little bit long. I want to close out by thanking all of you for your presentations today and for your willingness to share your slides with us. I'll post them on the AAS 238 press kit as soon as I've got them all. I want to thank Christine Pulliam and Hannah Braun for their extensive work in putting this whole thing together and for collaborating with me to find a good time to put it on during the meeting. And I want to thank all the audience that attended. We had quite a few people attending via Zoom and quite a few more attending via the YouTube live stream. I want to thank also the sponsor of our press office, University Space Research Association. That's the USRA logo that you see in addition to the AAS logo. They've been very generous in supporting refreshments at in-person meetings and helping to offset the cost of doing all this streaming for these virtual meetings. I also want to point out that we have a full program of 2 more press conferences tomorrow. The first one is at 12:15 p.m. Eastern Daylight Time. It's a twofer. The first set of presentations will be on the subject of fast radio bursts, and then we'll switch over to the final topic for our press conferences at this meeting, exoplanets and brown dwarfs. We'll have a couple presentations tomorrow at 12:15 and a whole slate of additional ones at 4:30 p.m. Eastern tomorrow. So I hope to see you all for those. And with that, I will close it out. Thanks all. Christine, did you want to say anything, any final words, or Hannah?
Nope, just a reminder to go to webbtelescope.org for even more about the cool science of Webb.
Yep, I'm going to add that link to the press kit too. All right. And to the Science Writers Guide, the media guide that you put together. So it'll all be in one place. Very good. Thanks, everyone.